Hello guys, in this video, I'm going to summarize what we already covered during our lectures for chapter number 2, which is properties of pure substance. Before I'm going to discuss the contents of chapter number 2, first of all, I would like to recap here. During our chapter 1 lectures, we already discussed about let's say we have a thermodynamic system. The thermodynamic system over here can be compressor, can be refrigerants, and etc. And then we're going to have a boundary. And then we're going to have a surrounding. So in order for us to characterize or describe our thermodynamic system over here, we need to determine its properties. So we need to know the properties of thermodynamic system. The properties of thermodynamic system include temperatures, pressure, internal energy, enthalpy, specific volume, density, and etc. So, and then take a look at the title of this chapter. We're going to determine the properties of pure substance. And then you should ask yourself, what does pure substance means? So in this case, for this chapter, we're going to consider, let's say, this is my thermodynamic system. And then inside my thermodynamic system here, it consists of water. Sometimes, I can also have thermodynamic system which is consists of methane gas, oxygen, and etc. Because the thermodynamic system over here is consists only one component, which is water, or methane, or oxygen. Therefore, this is what we call a pure substance. And then you should ask yourself, does all thermodynamic system is only consist one component only? And then the answer will be no. Sometimes you can also have a thermodynamic system for which is consists of oxygen, and then they have a nitrogen inside the same system. So this is what we call a binary component. It is no longer a pure substance because it consists more than one component. So this one will be covered during our lectures for chapter number 8. And then for the thermodynamic system, usually, commonly, it contains a water. Sometimes they also contain refrigerants, R134. For the part 1 of the chapter number 2 here, we're going to learn on how to obtain or how to determine the properties of the pure substance, which is either water or refrigerants. In this case, we're going to use a steam table. All right. In order for you to use a steam table, first you have to understand the concept of the phase change. Okay, let us start with let's say I have a piston cylinder. So say here, I have a piston, and then I'm going to fill my cylinder over here with water. So it's going to consist of liquid water molecules. Look something like this. So let's say I'm started with the temperatures of 25 degrees Celsius or at the room temperatures. And then I'm going to heat up my water inside the piston over here so that the temperatures will be rising. So now I'm going to have So let's say here temperatures equals to 70 degrees Celsius. I keep on heating up the water inside the piston cylinder over here until the first molecule of liquid water is converted to vapor. So now I'm going to have, because this one is a liquid water. So once I heat up until I reach temperatures of 100 degrees Celsius, the first molecule of liquid water was actually converted to vapor. So now I'm going to have this condition. So I keep on heating up my piston cylinder over here until more water vapor are actually forms. In this case, the temperatures was actually maintained at 100 degrees Celsius. And then I'm continue to heat up my piston, the water inside the piston cylinder over here until all the liquid water over here was actually converted to vapor. And then the temperatures was still at 100 degrees Celsius. And then if I'm going to continue heating up my water inside my piston cylinder over here, now I'm going to have look something like this. So going back to here, if you notice that between this is what we call, if you still remember, during our chapter 1 we did learn about the state. So let's name it as state 1, here at the state number 2, here at state number 3, here state number 4, here state number 5, and then here at state number 6. So if I'm going to plot my PV diagram or TV diagrams, so my diagram will look something like this, yeah. So this is my temperatures, this is my specific volume. So initially at state number 1 over here, I'm started with a liquid at 25 degrees Celsius. So let's say this is my state 1. So this is 25 degrees Celsius. And then I'm going to heat up. So because I'm heating up, the temperatures will be rise. Look something like this. So most probably this is my state number 2, which is at the 70 degrees Celsius. And then someone might ask, yeah, how do I know that the V here or the specific volume here also increase between state 1 and state number 2? Going back to the diagram over here, you should note that so imagine that I have a piston cylinder over here. First, I'm started at 25 degrees Celsius at the room temperatures, and then I'm heating up my water inside the piston cylinder over here. So common sense should know that once I heat up here, the piston over here is going to move up, meaning that the volume is going to be increased. But then I also do know that the specific volume was actually equals to volume divided by mass. But then the mass of the water here is not going to be increased because there's no mass flowing into the system here. Therefore, the mass is constant. This is constant. And then the volume, once the temperatures was increased, the volume also going to be increased. Therefore, my specific volume here is going to be increased. That's why I'm getting a graph look something like this. So let me erase this one. Until I reach at 100 degrees Celsius, and then this is what we call state number 3. See, state number 3 is for which the first liquid water was actually converted to vapor. So this is state number 3, and then I'm going to heat up because the temperatures are constant. So now I'm going to reach at state number 4, for which the state number 4 here, I'm going to have a mixture of liquid water, which is here, and also water in the form of vapor. And then until I reach its state number 5, for which no more liquid water, but all the water was in the form of vapor. And then I'm going to heat up, therefore the temperatures will be rise. So let's say this is my state number 6. So this state number 3 here is what is known as saturated liquid. State number 5 over here is what we call saturated vapor. And then we have state number 4 here. Of course, we're going to have a saturated liquid vapor. And then state number 6 here is what we call superheated steam, meaning that all the water is no more in the form of liquid, but all in the form of steam. So let me redraw it to make it much simpler. So now, if I'm going to draw temperatures versus specific volume, I'm going to have a graph look something like this. This is my state 1. This is my state number 2, which is saturated liquid. And then this is state number 3. And then I'm going to have state number 4, which is superheated steam. And then do note that if you notice that I'm not going to introduce wake into the piston over here, meaning that the pressure was actually at the atmospheric pressure. So the pressure is actually equals to 1 atm for the whole process. P equals to 1 atm. So meaning that this one is the process at the constant pressure. So if you're going to use, let's say you want to find what is the properties of the water at point number 2 over here, you have to use steam table. State number 2 and 3, which is table A4. This one is going to be table, I think table A6. This one is a superheated steam, which is table A4 or table A5. And then this one is going to be table A6, which is a superheated steam. So by knowing at which state actually your system is located, then actually you can determine what is the properties of the of that particular state. So I'm not going to show you on how to read the steam tables there, but then if you are required my help on how to read the steam table, actually how to read steam table should be straightforward. But let's say you need my help on how to read steam table, do let me know, and then I can provide you with another video on how actually we're going to read the steam table. So now let me redraw it. So now this is my TV diagrams look like. So let's say I'm going to run it at the atmospheric pressure, and then I'm going to have look something like this. So this is pressure equals to 1 atm. So what happened here, if let's say I'm going to put a wakes into my here, therefore the pressure will be increased. So let's say now instead of the pressure equals to 1 bar or 1 atm, I'm going to put some wake so that the pressure also going to be increased to the system over here, so that the pressure here is not going to be 1 atm, but it's going to be 2 atm. So now I'm going to have the same trend as this one, except that now I'm going to have look something like this. So now this one is what we call P equals to 2 atm. And then I'm going to run for 3 bar or 3 atm. I'm going to get something like this, 4, 5, and etc. Until at certain point, you actually don't have saturated liquid vapor look something like this anymore, but you have something like this. As you can see here, there's no changes of, meaning that from liquid, it started to change to the superheated straight away instead of changing to the saturated liquid vapor. Saturated liquid vapor. So yeah, it is important for you to understand this one on how I'm being able to come out with this type of graph. Means that I'm started with the liquid water, and then I'm going to heat up. Going back to this diagram, you can refer to the textbooks too. So once I heat up my water inside the cylinder over here, the temperatures will be rise. So see, the temperatures will be rise, and then someone may ask, how do I know that the V also is going to be increased? As I explained before, because of the specific volume was actually equals to mass divided by volume divided by mass. Once you heat up something, the volume is going to be increased. Even the common sense should, by using a common sense, you should know that once you heat up something in a closed container, then the volume is going to be increased. That's why I got an increased specific volume over here. And then until once, let's say I'm started with the 6 liquid water. See, I got 6 liquid water. After some time, so because I do know that boiling point for water at room temperatures, at room and 1 atmosphere, the boiling point was actually 100 degrees Celsius. That's why I know that it's going to be 100. At 100 degrees Celsius, one of the liquid water here is going to be converted to vapor. So this is what we call saturated liquid. See? And then I'm going to heat up. So instead of only have one water vapor, now I'm going to have a mixture of liquid and also vapor. So because I have a mixture, then I have to consider the steam quality or X. Steam quality was actually equals to, you know, mass of liquid plus mass of vapor. And then that one you should learn during your lectures, yeah. And then also for the steam quality over here, because here we're going to have a steam quality, right? X. So the X here also covered during your lab for experiment number 5 and also experiment number 8. And then going back to here, instead of having a mixture, now I have all the liquid water in the form of liquid was actually converted to vapor. So this one is what we call saturated vapor. And then if I'm going to heat up, then the temperature will be start to rise again until it reach what we call a superheated steam. Alright. So this one, you need to do some exercises here. I'm going to provide you a couple of video on how to attempt the question which reflects on the final and also in the test, yeah. So going back to the TV diagram over here, so let's say I'm started with the 1 atmosphere. The pressure is constant at 1 atmosphere, so I'm going to have a try and look something like this. Let's say I'm going to repeat, but then this time I'm going to use a different pressure. Let's say I'm using 2 atmosphere, so therefore I'm going to have look something like this, and then I'm going to repeat it again, but then this time I'm going to use 3 atmosphere. So until certain point for which I can no longer see a saturated liquid vapor lines over here. See over here. So this is what we call critical pressure and also critical temperature. So by plotting this line, actually I'm going to able to draw, this is what we call a saturation line. So usually during the condition here, sometimes we just draw something like this, and then sometimes the process looks something like this. So P equals to 1 atm. So let's say this is my state 4, state number 3, state number 2, and then state number 1. So let's say I want to find the enthalpy. Yeah? Enthalpy here was actually equal to HF from the steam table HF, and then here is going to be Hg. So you can find it from steam table. But going back to the same diagrams, yeah, let me redraw the same diagram. T versus V. So this is my saturation line. So let's say this is my process, right? So I'm saying that I'm started with the liquid water. I'm going to heat up my liquid water until the first liquid water molecule was actually converted to vapor. So this is my state 2, or we call it saturated liquid. And then I'm going to continue with the heating until I'm going to have a mixtures, meaning that now instead of only have one molecule water vapor, now I'm going to have a mixtures, meaning that I have, let's say, 5 liquid water, and then another 5 will be in the form of water vapor, until all the liquid water was actually converted to vapor. So this is my state number 3, and then I'm going to continue with the heating until I reach a state for which we call it superheated. So sometimes in the test or in the final, sometimes it's not necessarily the process to be started from here until here, heating up until here, until here. Sometimes the process can also started from superheated, meaning that this one is going to be my state 1. Let's say I have steam or superheated water at certain temperatures and pressure, and then it was cooled down, meaning that the temperatures will be reduced until it reached a certain point for which the first, this time is going to be the first water liquid water was actually being formed, and then sometimes it stopped at here. So it's not necessarily for the question to be start from here, going up to here, here and here. Sometimes it can also started from here, going back to here, and then started from here. It stopped at here. So you have to really understand it, because let's say you want to find the properties at this state. So you should know that this is what we call superheated. And then for the superheated steam, you have to use a table A6. If I'm not mistaken, it's table A6. And then if you want to find a properties for the saturated liquid vapor, meaning that the mixtures of liquid water and water vapor, then you have to use table A4 and table A5, while this one usually we use table A6. It's very rare for us to find the table, use table A6 here. So yeah, that's it for this chapter number 2, part 1. I hope that this video will help you to have more understanding on these chapters, yeah? Because this chapter is not that difficult, but then you have to understand about the concept of the phase change. Phase change meaning that, see, we started with the liquid water in the form of liquid, and then if you're going to heat up, and then now you're going to have usually we use a form in the terms gases, but then usually for the water we're not going to use water gases, but then we're going to use a vapor. So now if you're going to heat up the liquid water here, now after some time you will have a water in the form of vapor or gases. But usually it's very rare for us to use a term gases for water. For the nitrogens and etc., then you can use a gases, but then usually for the water we just use a vapor. Alright, I think that's it. Hope that this video will help you to understand on these chapters, yeah.